In fact, I'll start exactly by summarizing where we were last time. So what we discussed last time is that quantum invariance of a simple E group G on a three-manifold M can be computed by counting solutions of a certain system of nonlinear PDEs with gauge group for Langlands or geometric dual group on the four-manifold M times R plus. Thanks. And if there's a knot, the knot simply lives at the boundary, M times R. So the equations you have to solve are equations for pair A and phi, where A is a connection on a G dual bundle E dual over X.
I think
Does it?
it doesn't work or something.
This one actually does work. The one that doesn't work, it has a very short half-life, is this one.
No, but I think it's power, maybe it's power off.
Okay. You can see this, can't you? So, the equations you have to solve are equations from pair A and phi. And you can write the equations like so. So, they are elliptic differential equations, modulo the gauge group. Star is the knowledge star. And as I explained last time, you can think of these equations in terms of gradient flow for the complex Chern-Simons function. And that's why they can be used to calculate quantum invariance of knots. But today we go in a different direction. So the boundary conditions depend on the knot, as I've tried to suggest in the picture by placing the knot inside the boundary. But the details of the boundary conditions are a little bit subtle, and we'll talk about them later. However, the boundary conditions at the infinite ends are more simple. They're simply that A plus I phi must approach a complex value flat connection. Exactly what we do depends on what we want, but in one very important case, there's a simple recipe. If M is just R3, so that we're setting knots in R3, a flat connection is gauge equivalent to 0, and we just require that everything is 0 at infinity. For today, that's the only case we're going to talk about. Now, with M being R3, all we're doing is repeating what we had last time. So we study quantum knot invariance by solving certain equations in this situation. When the boundary is R3, the difference between the gauge group G of the Chern-Simons theory and the dual group of this description is important primarily when they have different Lie algebras. Since, for example, there's no second Stiefel-Witten class to distinguish SU2 from SO3. So the difference between a group and a dual group is most important if one of them is an orthogonal or spin group of odd dimension, and the other is a symplectic group, or vice versa. And we actually will see that something very interesting happens precisely when G is spin to n plus 1, for some reason. To compute quantum knot invariance, we're supposed to count the solutions of the KW equations with fixed incident number n. The incident number is defined in the usual way as a curvature interval over a four-manifold. Here trace is in a very quadratic form, which we normalize so that if x has no boundary and the group is simply connected, then n is an interval. For example, in the case of SUN, little n would be the second Chern test of the bundle E. Just as in Donaldson theory of four manifolds, or in the A model of top two-dimensional topological filtering, when we count solutions, we count them with signs. The sign with which a given solution contributes is the sign of the determinant of the linear elliptic operator that arises by linearization around a given solution. For physicists, this is the fermion determinant. Let P sub n be the number of solutions of instant on number n. Then, given these numbers, you form a series in a variable q. We expect that the bn's manage for all our finite many values of n, although that hasn't yet been proved. Given this, the series is a Laurent polynomial in q, well, times the fractional power of q, as I'll discuss shortly. And the claim is that this series agrees with the quantum knot invariant computed by other methods. For example, if G is SU2 and the knot is labeled by the two-dimensional representation, then Z of Q is the Jones polynomial. In all of this, as I keep telling you, the knot is encoded entirely in the boundary condition. The incident number was defined so that it's an integer of x is compact and without boundary, but our form manifold doesn't have this property, and to make n into a topological invariant, we require trivialization at both the finite and infinite ends. The trivialization at the infinite end comes from the fact that everything goes to zero there, but the trivialization at the finite end comes from the boundary condition that I haven't yet described. With this boundary condition, n is offset from an integer in a way that only depends on the knots ki and the representations ri that label them. So because of this offset, Z of Q is not a Laurent polynomial in Q. It's Q to the C times the Laurent polynomial, where C is determined by the representations. Given this description of the Jones polynomial, I want to explain why the Jones polynomial is related to a homology theory. I should say that the original explanation by physicists of how to relate the Jones polynomial to what mathematicians call a homology theory was by Ugri and Gukov. In this case, they defined vector spaces associated to knot. And then, after covalent homology was introduced, Gukov, Schwartz, and Gukov related this construction to covalent homology. What I've done is to make a construction parallel to those in gauge theory language. Probably the arguments are more self-contained, though it's hard to make that completely clear in just 2 lectures. The construction is more uniform for all good GA representations are, and I believe that the output is something that can be understood mathematically even without a full understanding of the quantum field theory. I should say that my proposal for covalent homology is qualitatively similar to some other ones, and also that I got a clue from work of Caltech and Cambridge. So, well, unfortunately, this is a very long slide, but we'll go through it bit by bit. I'm not sure if I can say anything to help those who are just coming in and catch up. We're starting from where we were last time, that the quantum knot variance for a knot in R3 can be gotten by counting solutions of the KW equation in this form of R3 times R plus.
Okay, I have a question. Is the knot actually going through time or just?
No, the knot lives in the boundary, as I've said a few times. So, the KW solutions, let S be the set of solutions of KW equations. It's expected, but hasn't yet been proved, that for a generic embedding of a knot in R3, the KW equations have only finitely many solutions, which moreover are non-degenerate, meaning that the linearized operator has no kernel or co-kernel. Well, brutally, we define vector space curly V by saying that for every solution there's a corresponding basis vector. Then we define 2 operators acting on curly V. Physicists would call them conserved quantum numbers. One of them is the incident number, which I'll call P, and then there will be fermion number, which I'll call F. I've already defined the incident number. It takes values in Z plus C, where C is a fixed constant. That only depends on the representations. So all these basis vectors have the same C, but different integers. The fermion number F is another integer value quantity. We consider the state I to be bosonic or fermionic, depending on whether it has even or odd F. The operator that distinguishes bosonic and fermionic states is then minus 1 to the f. F will be defined so that if a solution contributed plus 1 in counting KW solutions, then the state has even f, and if it contributed minus 1, then the state will have odd f. Let's see how we would rewrite the Jones polynomial in this language. Gaining nothing, at least initially. So the Jones polynomial was this, where a solution with instanton number ni and fermion number fi contributes minus 1 to the ni to b sub ni, and therefore its contribution to the Jones polynomial is this. So, and a formula equivalent to this one is that the Jones polynomial is the sum over solutions of the contribution of each solution, and trivially we can write that as a trace in this vector space that has bases corresponding to solutions. In this trace I've introduced the operator p that multiplies the state I by its instanton number. So we've rewritten the Jones polynomial as a trace, but we haven't done anything. We've just shuffled things around. However, on this space B, there's going to be more structure. On this space B, there's going to be a differential Q, which is an operator that commutes with instanton number, but it increases fermion number by 1, and it also obeys Q squared equals 0. That means we can define the cohomology of Q, the quotient, which is the kernel of Q divided by its image, and I'll call that curly H. This cohomology is supposed to be the Kovanov homology for those groups and representations where the Kovanov homology has been defined. It's automatically Z times Z graded with the two gradings given by P and F. The importance of passing from V to H is that H is a topological invariant that only depends on the knot, and not the way it was embedded in R3, but V is not. If you deform a knot that's embedded in R3, solutions of the KW equations will appear or disappear, so V will change, but H will not change. H will be an invariant of the knot. Instead of defining the Jones polynomial in terms of V, as we did by a trace, we can define it as a trace in the cohomology. So, well, the fancy way to say this is that the Jones polynomial is an Euler characteristic, a trace in which bosonic and fermionic states cancel in the cohomology H. The reason we can equally well equate Z as a trace in the space of all states, or the space of physical states H, is that in passing from V to H, pairs of states disappear and they make canceling contributions to the trace. In other words, if I and J are two solutions, such that Q maps one of the states to the other, then these two states have the same P but have F differing by 1, so their contributions to Z cancel. So in here they make canceling contributions, but here we omit them. When we pass through the cohomology, we omit those two states whose contributions to the trace cancel. Now, defining the Z times Z graded vector space H, and not just the corresponding function, adds information for two reasons. One is simply that since H is Z times Z graded, a state in H has a Z value fermion number, the eigenvalue of F. But we only remember F modulo 2 when we pass from the homology to the Jones polynomial. The second reason is that we can define natural operators acting on H, and how they act adds more information. For it to make sense to define the action of operators, we need a quantum Hilbert space for the operators to act on, and not just a function Z. I'll explain how to define operators later on. The ability to do all this depends on some facts about the KW equation, which were also discovered independently by Hayes.
When?
About 2 years ago. I think I'm going to explain the physical picture for a bit. I don't have slides for it, so unfortunately we have to turn off the projector for a moment and lift the screen. And we'll use the blackboard for a bit.
Maybe the other side must. Oh, the other. Oh.
But we also have to turn off the projector.
Yes, again.
How do I say this?
Again, press the same twice.
It's the same button, yeah.
You would like on the blackboard?
So we started with term assignments on M. And then, purely formally, we changed the integration cycle to a Lefschetz M. So now we want M times R plus with the Lefschetz symbol. That could have been a purely formal construction which we couldn't have said anything about. The reason we can say something about it is that this can be interpreted as localization in n equals 4 superangles. Now we know n equals a lot about n equals 4 superangles, so now we can do something. Namely, we have S duality, which yesterday I called electromagnetic duality.
Can I ask a question? And then, when you do localization of cold-foil superangles with very specific boundary conditions,
Yes.
which would break how much supersymmetry?
If there are no knots, the boundary conditions are, if there are no knots and the boundary is flat, the boundary conditions are half BPS. They're very specific. Well, if there are no knots, the whole story is a little bit surprising and much too elaborate to fully explain now. But to just tell you a couple words, if there are no knots and the boundary is flat, then the boundary condition is just the boundary condition of the D3 NS5 system with the theta angle, which was analyzed by Alberto and me. And its S-goal is therefore that boundary condition of the D3 D5 system, which a lot of people, including Alberto and me, have studied. So here it was D3 NS5 plus knots, which I haven't told you about, plus a theta angle. A lot of people study the D3 NS5 system, but usually without a theta angle. It's still half BPS with the theta angle, but it's tricky. It's one of the things we did, and I won't have time to properly explain it today. But here, we just have D3 NS5, sorry, D3 D5. I'll talk about it later. It's something a lot of people study. Now, here we're counting solutions. But just as in the last lecture, okay, once we get to D3, D5, we can do T duality to D4, D6. So if we just did T duality, what would it mean? Well, T duality would now, the picture would be this times a circle. And having a circle means that you take a trace. So it means you take a quantum over space and then take a trace. So in this picture, we count solutions.
Can you give us the dimensions? That was M3, and this is what?
Here we're in 4 dimensions. So we started in 3 dimensions. This is 4 dimensions, this is still 4 dimensions, but here we're in 5 dimensions. Just like last lecture. We're doing 5-dimensional superangles. But there's a difference from the last lecture, which is that it's 5-dimensional superangles with twice as much supersymmetry. So it really is a reduction from a 6-dimensional conformal field theory that's behind it.
But it still has a boundary, right? So.
Yes. It has a boundary. It's D4, D6. It's D4 right down there D6. But when you, when you go to 6 dimensions, there's no boundary. But if you ask me about that at the end, I'll explain it, but I don't explain it. So, when we make the T duality to D4, D6, there's a circle. Now, a path integral on a circle times something is a trace in the space of physical states associated to that something. For mathematicians here, let me say that mathematicians talk about categorification a lot, and it comes from all over the place. But to physicists, categorification has a uniform explanation. It always means you derive a theory from a theory in one dimension more. Such as we're doing here. Why introduce the extra dimension here? A circle means we take a trace. But as you saw, just the fact that we interpret this as a trace didn't add much. A solution here, we just declared was a basis vector here. In other words, a classical solution here becomes a time-independent, if S1 is time, a time-independent classical solution here. And a time-independent classical solution is a classical solution, classical approximation to a quantum ground state. So what I called V was the space of classical ground states. And what I call it on the slides H is the space of quantum ground states. So to go from V to H, we want to go from the, and the reason that quantum ground states are in rings is the standard reason in topological field theory. There's a supercharged Q whose square is 0, and the relevant part of this stress tensor is Q of something. So when you change the embedding of the knot, you're changing the theory by Q of something. It's really the same theory modulo Q. So therefore the space of quantum ground states doesn't change. So there's an invariant space of quantum ground states which had V as a classical approximation. To go from V to H, we have to calculate quantum corrections to the classical picture. Now I'm going to go back to the question that Maxim asked me, which was how much supersymmetry there is. So there were 16 supercharges, but even if the boundary is flat, it broke half, leaving 8. And then the knot generically only leaves 2 supercharges. And so we're doing quantum field theory with only 2 supercharges, which it's a gigantic version of what you can think of as quantum mechanics with 2 supercharges. So quantum mechanics with 2 supercharges leads to Morse theory. So, yes? Well, I think you saying. So in Morse theory, you have a target manifold and a Morse function, and there are critical points which give approximate classical ground states, and then you tunnel between them to find the quantum answer. So here, the manifold is the space of all 4-dimensional gauge fields. I'll tell you in a little bit what the Morse function is. The critical points are these classical solutions that we've encountered. And then the quantum corrections that we're going to need to go from V to H are the usual ones in the supersymmetric approach to Morse theory. What was the question?
So 4-dimensional theory, it's a Langland's twist, right, of 4D theory.
It's what twist?
I mean, Langland's, it's what you consider this Kapustin, right?
Oh, we call it the geometry, yes.
Yeah, okay.
Right.
And so what is exactly 5-dimensional lift of the theory?
Well, it hasn't, well, it isn't much studied because it's not covariant in 5 dimensions.
Yeah, but that's why I'm asking,
So
because does it exist or not? Because
well, it exists in the sense that the 5-dimensional theory exists. You take the same supercharge. You can still do localization. You do get an elliptic differential equation.
Okay.
Let me tell you. It's an elliptic differential equation that I'll describe when we go back to the slides.
But is it a covariant 5-dimensional
Well, I'll tell you what symmetry has. But it only has 4-dimensional covariance to give a quick answer. So we will be citing a 5-dimensional twist that only has 4-dimensional symmetry. That last fact has protected it from being much studied.
Okay.
Prior to
But what do you believe? Can it be covariantized? No.
But Kavanagh homology is a theory that has 4-dimensional symmetry. And I'll describe it by a theory that has 4-dimensional symmetry. I'll describe Kavanagh homology, which has 4-dimensional symmetry, by 5-dimensional equations that have 4-dimensional symmetry. For what it's worth, the boundary also only has 4-dimensional symmetry. Right? So we're in 5 dimensions, but because of the boundary, we can't possibly have more than 4-dimensional symmetry. But we will have equations that break 5-dimensional symmetry down to 4-dimensional symmetry, even away from the boundary. But they're respectable PDEs. They're elliptic modulated gauge field. Okay, let's try it. Okay. So I think I'm going to now continue with the slides. Although, sorry, nothing happened with the aggressive. Oh, sorry, press the one button. Actually, we have a little refinement while we're up, so we can chat a little bit more. If anything, we can chat a bit.
This is already done, so
I've heard this in use, if you're a mathematician, you'd say that there's a massive amount that hasn't been done. But if you're a physicist, you'd say, I've written it all down in excruciating detail.
But when?
Oh,
When?
a couple years ago. So what I talked about in the first lecture was what I've done in the last 2 years. But yesterday and today I'm talking about what I did the 2 years before that. So there is something I'm doing currently, which we'll get to later, but what I've said so far, for quite a while, is something written up quite some time ago. So I'm going to state some facts, which you can state just as facts. But I kind of in the blackboard told you why they were true, or at least I told you why some of them were true. It had to do with the fact that you can integralize to 5-dimensional superangles, so you have to get something. But I didn't go into enough detail there to give a complete arbitrary explanation of all the facts. But now I'll just tell you some facts that actually are simple enough that you can justify them. If you suspect these facts are true, you can just check them again. So the KW equations are equations of the 4 manifold. We'll take the 4 manifold to be a 3 manifold times a 1 manifold. In our application, the 1 manifold is R plus, but that isn't important for the moment. Now, in the KW equations, one of the fields is a 1 form phi, so I decompose it as the sum of a part that's cotangent to I and a part cotangent to M. Now we're going to replace our 4 manifold X. You know, when I was on the blackboard, I forgot something I really meant to tell you. And it's harder to see because it's written in. But we realized that we got a circle, and then there was a trace. But there was one more step I really wanted to tell you, which is just uncompactify the circle. And then you have the Hilbert space without a trace. It's that last step where you really get information beyond the Jones polynomial. Because as long as you have a circle, you're just taking a trace, and you're only talking about a function. And that's the Jones polynomial. But when you decompactify a circle, there's a Hilbert space in which you can take a trace if you want to. But the Hilbert space has more information.
Decompactifying means taking inverse of color?
Yes. We replaced the circle by R. So what made me remember it was that here, I'm going to replace X by R times X. X is not any 4 manifold, it's a 4 manifold M times I. R, in our derivation, is the 5th dimension that we got by T duality. Except in the classical picture, I'm taking it to R, BR, well, T duality would have given us a circle. So R is a new time direction, parameterized by a time coordinate that I'll call T. Actually, in yesterday's lecture, the normal coordinate was sometimes called time, but we forget all that. That's demoted, it's just a space direction. Now the 5th direction is time. And actually, here I've called the normal coordinate y. But we replace the part of following the y direction by the covariant derivative d by dt everywhere that it appears in the KW equations. To be explicit about this, d by dt means what it usually means, the covariant derivative in the t direction, where phi y is reinterpreted as a sub t. Now, if you took a random differential equation involving phi y, this procedure would give you a differential operator, not a differential equation. But in the case of the KW equations, phi y only appears inside commutators and covariant derivatives. And the substitutions proceed as I've written here. A commutator with phi y becomes a commutator of dt with phi I, and that's a covariant derivative. Or a covariant derivative of phi y is a commutator with a covariant derivative, and that becomes a component with the curvature. So in either case, we can make the substitution of phi y with d by dt, and we still get a differential operator because these expressions here are of degree 0. That's enough to show that we get a differential equation, but a generic differential equation is bad. And generically, if we had a random differential equation for which this much worked, the substitution of phi y by d by dt would not give an elliptic differential equation. But in this particular case, it actually is elliptic. And that's what really makes the story work. The 5-dimensional PD obtained by this substitution actually is elliptic. If you're convinced it's true, it's a very short calculation to prove it. This 5-dimensional equation has a 4-dimensional symmetry that isn't obvious from what I've said so far. So, we started on this kind of 4-manifold, and since we split X as a product, we lost the 4-dimensional symmetry of X, but we retained 3-dimensional symmetry of N. In other words, N was any oriented 3-manifold. And then, by replacing phi y with d by dt, we replace X with y times r times n times I. But it turns out that here we get back 4-dimensional symmetry. Namely, r times n can be replaced by any oriented 4-manifold Z, and our 5-dimensional equation can be naturally defined on Z times I. Not on any 5-manifold, but on this kind of 5-manifold. Actually, a little bit more general. As Hayes explained, it can be defined in any 5-manifold with a 1-dimensional foliation. Not necessarily a global product. At a certain point, we'll make use of this 4-dimensional symmetry. Another crucial fact is that the 5-dimensional equation is a gradient flow equation for a certain functional gamma of phi. I've just schematically combined all the fields into phi, and there's some gamma such that the 5-dimensional equations can be written like this. Now, I kind of told you during the period when we were working with Blackboard, from physical terms, why that's true. We're discussing a twisted version of 5D angles, and it has 2 supercharges. So, if you split off the time direction, that is, it has 2 supercharges, and it's a gigantic version of supersymmetric quantum mechanics with 2 supercharges. And a very large class of quantum mechanics problems with 2 supercharges can be understood in terms of Morse theory with some Morse function, which I'm here calling gamma. And the condition for supersymmetry is a gradient flow equation. So, I didn't completely prove why our supersymmetric problem was in that class, but this is so widespread in quantum mechanical problems with 2 supercharges that if you're a physicist familiar with that stuff, you shouldn't be surprised to be told that this problem was in that class. That means we're in the situation explored by Flohr, wanting to find 4 cohomology in the 80s. Modulo analytic subtleties, we can define an infinite dimensional version of Morse theory with gamma as the Morse function. So, I've stated this in mathematical language, but on the Blackboard we had it in physical language. So, okay, I'll continue with the math language for a little bit. In Morse theory, we define a complex, which is a fancy way to say a vector space, V, with the basis vector I for every critical point. And then we define a differential by counting instantaneous solutions that involve transitions from I to J. So for each pair of critical points, we count instantaneous that start at I in the past and end at J in the future. And then Q acting on I is a sum over all J of an instanton amplitude for transition from I to J. Now, in the physical picture, I corresponds to a time-independent solution, which is a classical approximation to a ground state. But the way we got the 5-dimensional equations guarantees that the time-independent solutions are the solutions of the 4-dimensional KW equations. So V is the space where the Jones polynomial was a trace. And then I said in that space there's going to be a differential. That differential is computed by counting tunneling trajectories in 5 dimensions that start at I and end at J. There's a procedure in general in supersymmetric Morse theory for counting these trajectories, and that gives you what is the differential Q that acts on this complex. Q commutes with the instanton number P and increases the Fermat number by 1.
What's the imperfection in your paper?
What is what?
Your imperfection in your paper.
Oh, well, we can discuss that probably. But my treatment was far from being complete, and it was improved later. So, as I said, the matrix elements of the differential are obtained by counting what in our case are 5-dimensional solutions that interpolate from a KLP solution I in the past to another one J in the future. So the picture looks a little bit like this. The time direction is vertical. The R plus direction is horizontal. We look for a solution where everything goes to 0 out here. In the past, the solution is time independent, and it comes from a 4-dimensional solution I. In the future, it's again time independent, and it goes to a 4-dimensional solution J. And in between, anything might happen. But the anything is localized near the boundary because it's far away from the boundary. Everything goes to 0. So to compute the matrix element of the differentials, we count 5-dimensional solutions of this kind. Now, before discussing the boundary condition, I want to explain something nice that happens in Covalent homology for certain gauge groups. So in the study of Covalent homology for SU2, it's been found that there are 2 variants of the theory that people call even and odd Covalent homology. They're defined using a complex V that additively is the same in the 2 cases. Well, in this complex, one defines 2 different differentials, say Q plus for the even theory and Q minus for the odd theory. So they have different homologies, but either homology can be used to calculate the Jones polynomial. Because the statement that the trace of homology is the same as the trace of the full complex V is true regardless of which differential you use. So the fancy way people say is that there are 2 different categorifications of the Jones polynomial. Q plus and Q minus are congruent mod 2. So even and odd Covalent homology are equivalent if one reduces mod 2. Why would that happen in the present context, and for what Lie groups do we expect it to happen? I claim we should use the exceptional isomorphism that SU2 is the same as spin 3, and that this phenomenon will occur precisely if G is spin 2n plus 1. In general, the cohomology of a manifold B can be twisted by a flat line bundle L. Instead of ordinary cohomology, we can consider the twisted cohomology of values in L. The possible L's are classified by homomorphisms from poly 1 into C star. In the present case, B is a function space consisting of pairs A and phi in a 4 manifold. Well, we only care about such pairs belong to gauge transformations. And the boundary conditions tell us to only allow gauge transformations trivial on the boundary. And for m equals R3, it ends up that pi 1 of B is pi 4 of the gauge group, where pi 4 comes in simply because x is 4-dimensional. Now, this is pi 4 of the simple Lie group, and it classifies the possible variants of Covalent homology that we can make by twisting by a flat line bundle. So there's only one variant, in other words, the group 0 that only has 1 element, unless the dual group is a symplectic group, in which case there are 2 versions of the theory. So precisely if the original group was a S spin 2n plus 1, or S of 2n plus 1, the dual group has a non-trivial pi 4, and then there are 2 versions of Covalent homology. So from this point of view, Covalent homology is unique, except for this kind of group, or this one, in which case it has 2 versions. Concretely, an SP2n bundle of a 5-manifold Y with a trivialization on its boundary has a Z2 value invariant eta derived from this homotopy group. When we define the differential by counting 5-dimensional solutions, we have the option to modify the differential by weighting each solution with a factor of -1 to the eta. With this modified counting doesn't affect the fact that Q prime squared is 0. And since instead of counting the solutions with one sign, we're counting them with a different sign. That doesn't affect the counting mod 2. So we get a new differential that's congruent mod 2 to the old one. And that's our candidate for the 2 versions of Covalent homology for this kind of gauge group. Okay, I still should tell you a little bit about the boundary conditions, but maybe I'll stop for now in case there are any questions. So the boundary conditions are crucial because, for instance, it's only by the boundary conditions that knots enter. First, I'll describe the boundary condition in the absence of knots. It's essentially enough to describe the boundary condition in 4 dimensions once you understand that the lift to 5 dimensions is fairly obvious. And since the boundary condition is local, we can assume that the boundary is just R3, which anyway is our main approximation. That's right, our main application. So as a preliminary, we need to be familiar with Norm's equation of H3. Norm's equation is a system of ordinary differential equations for a triple of elements of the Lie algebra of G. Actually, unfortunately, G is what was called G Gould earlier. So Norm's equation reads like so with cyclic permutations. So on a half line, Norm's equations have a special solution introduced by Norm, where the T's are elements of G that obey the SU2 commutational relations. To get the Jones polynomial and its generalizations, we want the case that the T is to find a principal SU2 algebra in the central sequence. So this sort of singular solution of Norm's equations might look funny if you haven't seen it before, but it's actually been much studied by Norm, Kreinheimer, Atiyah, Bolevsky, and many others. We use it to define an exotic or elliptic boundary condition for our equations. So this has long roots. So, as a gauge theory boundary condition, it is the boundary condition that comes from the D3, D5 system. And the D3, D5 system has a long history, which I won't try to summarize now. As a boundary condition in gauge theory, it was described by Gaudier and me about 5 years ago. And ellipticity, as a physicist, you say it's got to be elliptic because the D3, D5 system makes sense. But anyway, with Reich-Mozio, well, at least in this particular point, I've turned over a new leaf. I know it's an honest fellow. You prove that the boundary condition is elliptic. That one makes sense. Now, Norm's equations can be embedded in KW equations. I'm going to use Norm's equations to define a boundary condition. We do it as follows. Norm's equations are actually a specialization. That's meant to be a large star, a little bit too large. Norm's equations can be embedded in the KW equations. If you look for a solution that's invariant under translations of R3, the connection vanishes, and the one form takes this form with a 0, then these equations reduce to Norm's equations. So the Norm pole gives a special solution, which is singular with the boundary. And we define an elliptic boundary condition by declaring that we only allow solutions that are asymptotic to this one as y goes to 0. And that's the boundary condition we want in the absence of knots. And as I told you, in a forthcoming paper, we're actually proving this elliptic. As I also said at various times, for the most obvious boundary condition for covalent homology, we require everything to go to 0 at infinity. With these conditions, one can prove that the Norm pole is the only solution on the half space. That corresponds to the statement that covalent homology of the empty knot is of rank 1. Okay, now I want to explain how to modify the boundary condition along a knot K. So that will be done by requiring a more subtle singularity in the presence of the knot. So the physical picture, to simplify, is that the knot is a boundary of a D2 ring ending on a D4 ring. And so that means the boundary of the D2 ring would be a 1 manifold, and a 1 manifold ending on a D4. It's a D2-4 ring ending on a D4 ring, and we're more familiar, it's a D1 ring ending on a D3 ring. And then that gives an 't Hooft operator, and it equals 4 superangles, which is represented by a certain singular solution. But here we're not using standard 't Hooft operators, because our 't Hooft operator is in the boundary where there already is a non-pole singularity. of the D3, D5 system. So the knot is described by a singularity that's a composite of an drift operator with the boundary, with the non-pole. So to describe that singularity, the local model is that the boundary is R3, and K is a copy of R inside R3. And we're now supposed to get a singular solution on R3 times R plus that along the boundary has the non-pole away from K, but has some other behavior along K. The model solution, moreover, is invariant under translations along K, so it can be obtained by solving some reduced equations on R2 times R plus. So the picture looks like this. Here's R2, and here's a half line R plus. The knot in the reduced picture is just a point. So we have some reduced equations on a 3-manifold, which have a non-pole generically along the boundary and exceptional behavior at one point. You can also assume some translation and scaling symmetries. So to describe the boundary condition in the presence of the knot, you need some special solutions of reduced equations. In fact, in gauge theory with the gauge group being G dual, we need one singular solution for every irreducible representation of G. So representations of the dual group are supposed to representations of G are supposed to classify singular solutions of G dual. So you can actually do this. It's possible to find the desired solutions in closed form. I did it in my paper for the case of rank 1, SU2 or SO3, and my student Michaela generalized this for all cases. I won't describe the necessary solutions today. I'll just remark that they're closely related. Well, see, I stated this already in physical terms. They involve the Hooft operators, but the Hooft operators living on top of the non-pole. The Hooft operators correspond to the geometric Hecke operators of the geometric line length correspondence. So a simpler version of this would be the singular solutions related to Hooft operators or geometric Hecke operators. The trick here is that you have to put that singularity on top of the non-pole. The model solution has a singularity that I've represented here in terms of a point in R2. But if we pull this back to 5 dimensions, we should describe it by saying that the point is of codimension 2 in R2, and then if we're in 5 dimensions, the boundary is a 4-manifold, and since the boundary is a 4-manifold, codimension 2 means that the singularity lives on a 2 surface. So in the 4-dimensional picture, we have a knot in the boundary, but in the 5-dimensional picture, the knot became a 2-manifold. A boundary condition in the 5-dimensional equations modified on a 2 surface is needed to define what are called the morphisms that in covariant homology are associated to non-cobordisms. So I've drawn a simple non-cobordism, but to make the picture easy to draw, I've started in the past with an unknown, and I've ended in the future with 2 unknown unknowns. Then I've drawn a simple surface, simple enough I could draw it, that starts at K and ends at K prime. And this is a 2 surface, which, as drawn, looks like it's embedded in R3, but you should really embed it in R4 in your mind. And R4 is the boundary of the 5-manifold. Now, there's another thing for which it's important. So we looked at the equations reduced to 3 dimensions because that enables us to find the right singularity that defines the boundary condition in the 5-dimensional equations. To compute the Jones polynomial, you need to count certain solutions in 4 dimensions. Knowledge of these solutions is also the first step in constructing the candidate for covariant homology. So how would we actually count 4-dimensional solutions? Well, there's a standard strategy often used in floor theory and its cousins, in which you stretch things in 1 dimension, hoping to reduce to a piecewise description by solutions in 1 dimension less. So here's the picture I've always drawn, but I'm stretching it. So here's the knot in the boundary, but we've stretched it, so it's very working this way. So now if we think that this direction is time, and admittedly, that's the third different thing I've called time in these lectures. Generically, this picture is almost time independent, but there are some times at which something happens. Two lines cross, or there's a creation or annihilation event. But you can hope to describe this, a solution in this situation, as being one which is generically time independent, except for some moves. So, in a standard strategy to describe the four-dimensional solutions, one first tries to describe the three-dimensional solutions, and then you try to patch them together to get four-dimensional information. A variant of this fact is, this point is as follows. Most mathematical definitions of the quantum homology proceed one way or another by defining a category of objects associated to a two-sphere, or a copy of R2, with labeled R points. So, we'd like to know what the category is in the present situation, and it turns out that it should be an A-model category of a modular space of reduced three-dimensional equations in the appropriate geometry. So, roughly, the appropriate geometry is like this. We have a two-manifold with points labeled by representations times a half-line. And we want to understand the solutions in the appropriate category is an A-model category that's associated to gauge theory in this situation. So, Gaeta and I were able in this paper to get a fairly clear picture of what should be the category. But it was tricky. For SU2, it's a Fukaya-Seidel category that from any model category with a superpotential, where the target space is the moduli space of one pulse or R3. And with a certain superpotential, it depends on the positions. I said positions of the knots, but it's really positions of these points in this picture. We were also able to get some understanding of how to relate this description of the Jones polynomial to more standard ones, without going through yesterday's quantum field theory arguments. I won't describe that completely, but I'll say a few words about it. There actually are a few tricks involved as well. I'm only going to tell you. So, let's recall that standard approaches to the Jones polynomial and Cabana homology usually begin by considering a projection of a knot to two dimensions. So that's the knot we started the first lecture with. And then we projected it to two dimensions down into the screen. So in the KW equations and also their five-dimensional cosines, there's a nice way to incorporate a knot projection by modifying the boundary conditions at infinity. Instead of asking that everything goes to infinity, to zero at infinity, we keep that condition on the connection A, but we change the condition on phi. Physicists call this moving on the Coulomb range. We pick a triple of commuting elements of the Lie algebra of the maximal torus, and we ask for phi to approach a fixed triple as y goes to infinity. We use the fact that the equations have an exact solution where A is 0 and phi is of this form. So it's consistent to ask that a solution does this at infinity, as well as giving the non-pole at 0. The counting of solutions of an elliptic equation is constant under continuous variations, under appropriate conditions. So one expects that the Jones polynomial can be computed with this more general asymptotic condition for an arbitrary choice of C. If G is SU2, the maximal torus is one-dimensional. So if C is non-zero, it's a fixed element of the Lie algebra times a vector in free space. So picking C essentially is picking a vector pointing in some direction in space. So the choice of A defines a projection of R3 to a plane. So this is now built into the construction. For G of higher rank, we could do something more general, but in this particular case, with C now being a regular element of T, seems to be sufficient. So I think that this is what one wants to understand knot invariance. One has an invariant description where C is 0, but one can also try to simplify it by building a knot projection by taking C to be non-zero. And one has an understanding of y, the simplified description, sorry, the invariant description with c equals 0 is equivalent to the description with the projection built in with non-zero c. Taking c sufficiently generic leaves a drastic simplification because the equations become quasi-abelian in a certain sense. Actually, in a sense not unrelated to yesterday, or the day before yesterday's Nobel Prize. The line scale greater than c, the structure group of the gauge group is effectively reduced to an abelian subgroup, and the equations, the solutions can be approximated by solutions of an abelian version of the same equations. There's an important locus where that fails, but it can be understood. So both physicists and mathematicians are familiar with such things. We scale up or not until the quasi-abelian description is therefore valid. And from this we were able to understand the origin of the vertex model with which I began yesterday's lecture. I think I'll stop here. Thank you.
Question?
There is any clear relation between your approach and Riemann Simons?
And what approach?
Riemann Simons.
Well, you see, in my opinion, the literature of Riemann-Simons needs to be rethought starting from the beginning. So the first step is that the Gukov paper needs a better explanation. So I think there would be. I think that to establish a clear approach, Riemann-Simons would have to be made more clear.
But at least you can take it as some modification of, a three-dimensional TFT.
I can't understand it well enough to do that, because to me, the explanations of the literature are not sufficiently clear. So, as I said about 20 slides ago, I reformulated the argument in the gauge theory language with more self-contained arguments. Now, I'm sure that the other approach can also be made clearer. And I believe if one did that, one would better understand the connection.
But there is no relation whatsoever with yours. Okay.
There is a relation, and it will be easier to formulate the relation well when the other picture is more fully explained. The other picture is older. I said that about 20 slides ago. That the original physics-based approach to covalent homology was by Ubri and Waffe, and then by Waffe, Schwartz, and Gukov. And you're essentially asking me about the developments related to that. So, one of the goals here for me would be to understand more completely the relation between the two. Personally, I think that the understanding isn't satisfactory. I personally think that to give a good answer to your question, the understanding needs to be improved. I regard discussions of refined terms to be obscure at the foundations. If you disagree, I'd love to talk to you later.
No, I agree. I tried to understand.
You agree?
Okay.
If you agree. You looked awfully puzzled when I said that. I thought you listened.
In that paper, they tried to make some comments in relation to your picture. They tried to make that it's somehow related, but I was confused very much. That's why I wanted to ask you. Because they claim there is some relation, but I couldn't figure out.
Morally speaking, I'm sure that there is. But there's a six-dimensional picture. Actually, I'd like to answer a question that I think you asked. Let's go back to the question. You asked me if there was still a boundary in 5 dimensions, and I said that in 6 dimensions there's no boundary. Yes, I'm sure. So, when you hear a lecture about 5-dimensional angles, such as mine or the one before me, you should ask, since 5-dimensional superangles isn't good, as a physicist, you should ask, so a mathematician might settle for the fact that the equations will work. But as a physicist would be suspicious of studying writing on elliptic operators. Even mathematicians are, because if you're a mathematician, ellipticity is great, but you still have to worry about questions of compactness. Right? So, the mathematician worries about whether the moduli space is compact, but the physicist would like the comfort of knowing it came from a well-defined quantum theory. That morally tells you possibly after writing 100 pages of inequalities to prove that the moduli space is compact.
But do you,
I'm being a little funny.
but basically, do you expect from your equations to be compact or not?
Not universally, but for this situation related to the non-invariance, yes. Actually, Cliff Downs has become interested. And you can find on the web 2 extremely long papers by Towns investigating compactness questions for the KW equations.
But I heard that something doesn't work, or what's the statement?
Without a boundary condition, the modular space isn't compact. You see, when a compact form manifold, most of them I completely described the modular space, it was not compact. In general, it's given by, well, it'll be compact on a simply connected form manifold. Because in a simply connected form manifold, we show the only solution is 0. That was compact. So, you don't get compactness for free, but sometimes you get compactness. Now, we can go a simply connected form manifold without boundary. The half space we need for the Jones polynomial is simply connected, but it has a boundary, so our proof doesn't apply. I expect the result to apply, but that hasn't been done. What I wanted to say then was so, when you hear a lecture with 5D angles like mine or less, you should ask what's the ultraviolet completion. And the answer is different for the two lectures. But for my lecture, the ultraviolet completion is in 6 dimensions. And so, our Kovenov picture was on this kind of 6 manifold, where X was 4-dimensional. Well, that was the 5-dimensional picture. But the 6-dimensional picture is on X times a 2-manifold that looks like this. It's a 2-manifold that has an infinite end. We could compactify the infinite end, just as I could have compactified our polynomial lecture. But I didn't want to, because there's no way to compactify it without introducing a discussion of what's happening out there. It just was simpler to give a lecture by letting that end be non-compact and say that everything was 0 there. 0 is much simpler than anything else I could have said. So, likewise, it could compactify the same, but we don't want to. It's easier to take a semi-infinite cigar, and it's got a uniform symmetry. And the cigar over U1 is R plus. So the 6-dimensional theory can be reduced to a 5-dimensional description by reducing on the U1 orbits. When we do that, by standard reasoning, we get 5-dimensional angles. Well, the reasoning is standard when the U1 acts freely. It's a little bit less familiar that if there's this kind of fixed point, then you get the non-pole behavior for the 5D image theory. In other words, I'm claiming that I'm making the following claim about a slight generalization of the usual 6D7. That the most familiar special case is that if you reduce on a circle, you get 5D angles. Well, having a circle means there's a circle symmetry. Suppose the symmetry doesn't act freely and has fixed points or semi-freely. Well, there are different kinds of fixed points in a circle action in 6 dimensions, but here we're considering the case that the fixed point set is a 4-manifold. And then the local picture is the same as here. And I claim that that's the picture that leads to the non-pole.
So what's exactly 5D theory? So you...
What's the 5D theory?
yeah.
The 5D theory is A equals 4 super plus.
So on the boundary, is the coupling going to 0?
I can't hear you.
Sorry, on the boundary, is the coupling going to 0 to 5D?
Well, no. Well, what motivates your question is that the radius is going to 0.
Yes.
So, let me explain the question, and then we'll discuss things further. So, there's this mystery in 6D3, which on a circle of radius r gives 5D in mystery with a factor of 1 over r. Okay, you actually had, your hypothesis was inverted actually. So in conventional dimensional direction we give a factor of r. But here, there's actually a factor of 1 over r. The fact that it's 1 over r rather than r is a very strong evidence of the fact that the reduction from 6 dimensions to 5 dimensions is non-classical. Classical dimensional reduction into integration of the fiber would give a factor of r. Here the answer involves a factor of 1 over r. So your question might have been, if the no, you're right. 1 over g squared is 1 over r.
Yeah.
So g squared is r. So if r went to 0 adiabatically, you would have known that the coupling would go to 0. But here r is running out right to 0 adiabatically. So we don't really have that kind of description. The description we have instead is the non-pole description. If you want to know how I know we have that description, it's because you can embed this star in a Talmud space. And standard reasoning says that under reduction of the circle, the Talmud space turns into D6. So the gauge theory is given by a D4, D6 system. And the D4, D6 system has been studied a lot. I'm going to stumble if I try to give the correct references now. So I have to apologize that I won't do that. But it's been studied a lot and it leads to this non-normal behavior. Any other questions? Yes?
So you, something always puzzled me is that you have John Palmer you interpreted from Kogan homology. But since you, in your original paper on John Palmer, you have introduced topological quantum flow theory for 3 manifolds or not in 3 manifolds. You have some version of Kogan homology that I don't have from just some cases.
I had trouble hearing the question, but I think the question was, could we do other 3 manifolds instead of R3?
Exactly.
Had we done other, we can try to, but we'd have to do more work, which hasn't been done. And it would be easier to start with a 3 manifold with a finite fundamental group. So if I was to do this, I would possibly look at RP3 next. Actually, I would look at RP3 minus some points. So if you like, I take the connected sum of R3 with RP3. Which topologically is RP3 minus points. Yesterday, there was a step when I said, well, that to express the Jones polynomial and its analog for any 3 manifold in this language, we have to know how to express the standard integration cycle as a linear combination of Lefschetz thimbles. And I said, for R3 or S3, you can skip that stage because it's simply connected, so there's only one Lefschetz thimble. But if we want to do another 3 manifold, we're going to have to express the usual integration cycle in terms of Lefschetz thimbles. I'm sure it's an extremely interesting thing to do. But at that point, after working with this stuff for 2 years, I went off and started working on string perturbation theory instead. So.
Yeah.
No one else has taken it up, so that's where we're going.
It's very interesting to study for hyperbolic.
Yes, but it might be very interesting, but it's going to be a lot of work. I would practice with RP3 first if I was going to work on it.
Sure.
And hopefully, I don't know much about it personally, but hopefully there are some simple statements about modes and RP3 that would help give one some orientation. RP3 is even in this world where you can apply localization for someone else. And that, I don't know what would happen. I've kind of said what I can say about it. Any other questions?